Good evening. I'll be presenting today how do you learn from your enemy, and this is a framework we developed for an adversarial multi-agent reinforcement learning, and demonstrating how we may learn adversarially. And this video here is a demonstration of what our framework can do, and it's presented by me, Kai Wen, and my fellow teammates Andrew, Zhenghao, Wei Jie, Ziyu, and Qirei. And so, what is this whole project, this AlphaTank project about, right? We say that, oh, it's black magic, let's make black magic come true. No. Well, what is it really about? It's about a full RL pipeline, right? We built our environment ourselves, end-to-end training, has low dependency. And the environments can be utilized by other researchers as well if they want to use a very simple framework to run multi-agent competition or collaboration settings. And we deliver a very unique learning environment, this adversarial learning environments for testing different RL algorithms' capability to learn in such highly dynamic environments. And also, we give them the opportunity to fight against human intelligence, and is also adjustable to test for suitable for curriculum learning or cycle learning setting. Okay, so let's see how this whole interaction happens in the environment. So the whole idea is we have the SD, the observation space. We give to our deterministic transformation. This essentially builds up some of our proprioceptions for this tank agent we have. And then also alternatively, it goes directly to the agent. So this is going to be our learning agent, this PPO. Currently we have PPO and SAC, but in the future we're developing more. And so we'll give the action, and same thing will happen for the alternative agents. Notice that this alternative agent may be a team or a single agent. So let's use single agent for simplicity. And so this alternative agent or bot will give this adversarial action, and adversarial learning will occur. So some quick backgrounds on the learning algorithms. The first one we're using is PPO. Essentially, it comes from policy gradients ideas in RL, and we have action as a policy. And then we have this GAE, the general advantage estimation. Essentially says about what's like how good your current action is, right? Not just state action pairs, but how good it really is for you to make this action. And then the very signature clip loss for policy gradient to avoid essentially like too big of an update on the gradients. And then similarly, the MSE essentially achieves sort of the TD table replacement for neural network, and then very standard that we add entropy cost. And similarly for SAC, follows action with the policy, very similar formulation, but then we do have replay buffer plus discretize, a little bit different. And then we have a soft queue, which is sort of probing the environment, avoiding overfitting. And then the last, notice that this sort of simplified expression is actually derived from RLS inference. It has a very deep mathematical roots, but we're not going to go into. This is just like a brief algorithm introduction. And then similarly, we have what we've seen previously in PPO. And then currently, again, SAC maximizes entropy, uses 2Q network. It's off policy learning. And then it's usually a little bit more computation heavier compared to PPO. We do use discretized environments because of how basically we are setting up our training, which I'm not going to go into the details too much. Okay, here we go. We're in the environment, and then the environment is very particular, interesting because we have different settings. We have obstacles of walls, we have the buffer zones, and then we have the debuff zones, which essentially is like buffs that agents can pick up, and the walls are part of the environment. And so we built this using Pygame, and then essentially adapted to an abstract class of OpenAI Gym for easy to interact with, and then we can compete in solo or in teams. So the MDP descriptions is the follow. You can see it's a very, very long list of observations, and if you're interested, please contact us or read our report as well. It's I think that we build up something a quite sophisticated proprioceptive systems, and essentially the agents are making discrete actions, movement, rotation, and shooting, and trying to compete in this environment. By competition means killing each other. And the key is that notice, though this is a discrete control, it turns out in reality to be very, very hard to actually train an agent to do um, proper actions, because once the agent hits the wall, usually um, it will sort of learn to rotate, right? So it try to not hit the wall, because hitting a wall will be a penalty. And then once they try to not hit the wall, and then if they still try to move forward, the RL agent essentially needs to learn how to move while drifting, which is, I would say, is quite complicated. And then while drifting, it also needs to know how to shoot, right? So it makes it even more complicated. So, but our system is an approach to try to tackle this problem to make it actually learn properly. Though the representation of the learning is actually very interesting, we'll see later. So again, here we introduce our reward engineering. I'm not going to go into the details. We have those in the report as well. But basically, there are different penalties, as simple as this victory, hit the wall. As I said earlier, there's going to be a penalty, being stationary, or the distance away from different agents. And a little bit more, bullet trajectory, if it dodges the reward, or the aiming, and then how many controls it's exerting, and the rotation that's it's given. So something aside, this framework is really good for cycle learning, which essentially we have this bot factory, and the bot factory give us this really nice ability to train our reinforcement learning agents against different bots. And this process can be deemed, it's sort of, we got inspirations from AlphaStar, from Google's AlphaStar, which essentially tries to fight against different experts and then gain experiences from it. So we sort of was inspired by that, and we built up this sort of cycle learning condition, trying to make an agent that is more robust and essentially being able to fight against all bots. And so yeah, we have sort of this whole system. Again, I'm not going to go into the details, but we sort of have this whole system going on with cycle learning. And similarly with curriculum learning, it's I would say in this condition, it's sort of a different form of cycle learning, and just building from easy tasks to harder tasks. And then we do have a 1DB report, and I'm not going to show it here directly, but you can find this report on our repo or on our project report as well. So I want to show this results, which I found it quite interesting, because this is sort of on the left. It's this our RL agent is this red one, and the bot agent is the smart agent, which essentially does a BFS in this blockage environment. And you can see that the RL agents, from the score you can see it as well, sort of kind of outsmart this bot agents by setting traps. It knows that it's going to chase the RL agents, and it just sits trap and waits for it to come, which is pretty interesting compared to like how we would think human heuristic would fight in this sense. So the key theme here is that sort of the reinforcement learning agents have learned a different representation, then a different way of tackling things. And similarly for here was aggressive agent, which essentially is a more aggressive BFS agent. It just rush to it like Terminator style, rush to it directly, and then try to kill the RL agents. And so the agent sort of learns to kind of play dumb in the beginning, and then lure the aggressive agents here, and then once it does, it sort of shoots a bunch of bullets and then rapidly goes around it trying to dodge from the aggressive bots bullets. And very interesting thing is that we have also implemented multi team playing in our environment, which supports many different agents. This is just a simplified example demonstrating how we have two agents trying to fight with two bots, which in here are both smart bots. And then yeah, basically we can try to do and then reason similar things. Like for instance, one of them I think was trying to use a rebound strategy to defeat the bot agent. So there's different representations being learned. We're still investigating into how they may collaborate together to try to defeat the agents. And then in this case, this is sort of one of the drawbacks we're currently having, which is that the agent learns really well how to defend itself while fighting back. So when there's no direct attackers like the bots showing here, it's sort of maybe needs a little bit more training times, or it needs a little bit more different reward function shapings. But yeah, it doesn't work as well when compared to when the boss is attacking them directly. So again, what we have delivered here is a full RL pipeline from the environment to training, all end to end with low dependency, and it's very customizable. And we have this unique learning dynamics happening here because we have this adversarial learning going on. And then showcases of how traditional R algorithms can actually use the characteristic of the environments, for instance, the buff zone and the debuff zone, how bullets can bounces, and then also characteristic of the opponents, for instance, how the boss agent will definitely chase the RL agents, and then use these characteristics to fight them. So again, this is what I said before. Something we're still tackling right now is maybe using psycho learning or curriculum and trying to make our agents a little bit more aggressive and trying to attack other agents. And then, yeah, basically seeing how we can quantify this gain of doing cooperation. How can we actually say that what the agents are gaining from cooperating together in like team settings? And just want to summarize up is that we find that not all actions are sensible. It doesn't make sense. Some of them like doesn't even fire when the enemy is right in front, but it does work, and it does outperform and outsmart the heuristic boss agents, which is pretty impressive. And it represents it feels like it represents something that the agent have learned. Something that is not just human intelligence. And this is like sort of quoting to how AlphaZero was developing how to play chess on its own instead of using human supervision. And this is our presentation, and hope you enjoy, and thank you for listening.